Welcome to the deep dive. Today, we're getting into decision trees and random forests. Pretty powerful tools for prediction.
Yeah, definitely. We've got some sources covering the basics, the good, the bad.
Right. And our mission today is really just to give you a solid feel for how these algorithms work and, well, why they matter so much in data science.
Think of them as ways computers learn to make educated guesses from data. We're going to break down that learning process.
Okay, let's start with decision trees. So imagine you're deciding about playing tennis based on the weather forecast.
Right, the classic example.
Yeah, so like if it's cloudy, you play. Simple. But if it's sunny,
Then you need more info, maybe humidity.
exactly. Normal humidity, game on. If it's rainy, maybe you look at the wind.
Weak wind, you might still play. Strong wind, probably not.
Perfect. That whole process, that's basically a decision tree. It's a visual map of decisions and outcomes based on conditions.
And what's really crucial is how the tree figures out the best questions to ask at each point. The best splits.
Ah, right. It's aiming for purity in the results down each path.
Exactly. Purity, which leads us to impurity measures.
Yeah, the tree wants the groups at the end of each branch to be as similar as possible, pure, like you said.
So we use things like, the Giannini index or entropy, mostly for classification tasks.
Like sorting those apples and oranges we talked about before. A pure group is all apples or all oranges.
Right. And for predicting a number like a price, you'd use variance instead.
Okay, so Gini and entropy measure the mix-up edness.
Kind of, yeah. Gini goes from 0 to 0.5, entropy 0 to 1. 0 means perfectly pure, no mix at all.
And higher values mean more mixed.
Precisely. Then there's information gain, also for classification. It measures how much clearer things become after a split.
So a bigger gain means the question was really helpful in separating things.
You got it. Higher gain is better. Helps the tree make smarter splits.
Okay, that makes sense for one tree. But the real power often comes from using lots of them together, doesn't it?
Absolutely. That brings us to ensemble learning, and specifically random forests.
Ensemble.
Yep.
Like a group effort. A committee of experts.
That's a great analogy. Instead of relying on one decision tree, you combine predictions from many. One key technique is called bagging.
Bagging. Bootstrap aggregation, right? What's the idea there?
Well, you take lots of random samples with replacement from your original data. So some data points might appear multiple times in a sample, others not at all.
Okay, multiple different versions of the data set.
Then you build a separate decision tree on each of these samples, just a standard tree using those impurity measures.
Then combine their guesses.
Yep. For classification, you take a majority vote. For predicting numbers, you average their predictions.
And this helps with overfitting, making the model less likely to just memorize the training data.
Exactly that. It tends to make the overall model more robust and generalize better to new, unseen data.
So random forests are basically just a bunch of these bag decision trees.
Pretty much. It's a supervised learning method, works for both classification and regression. You do the random sampling, the bagging part.
Build a tree for each sample.
Right, but here's the twist for random forests. When deciding on the best split within each tree, you only consider a random subset of the features available.
Ah, okay. So not only random data samples, but also random feature selections for splitting.
Yes, it adds another layer of randomness, which further helps prevent overfitting and makes the individual trees less correlated.
Then you combine all the tree predictions, voting, or averaging, like with bagging.
That's the essence of it.
Sounds powerful. I guess the main advantage is accuracy.
Generally, yes. They're known for high accuracy, handling both classification and regression well, and being pretty resistant to overfitting, as we said. Plus, they can even give you a sense of which features are most important.
Any downsides to consider?
Well, they can be slower to train than simpler algorithms because, you're building potentially hundreds or thousands of trees.
Makes sense. More computation.
And interpreting them. It's harder than looking at a single decision tree diagram. Understanding why a whole forest made a certain prediction is less intuitive.
Right, the black box problem can be a bit worse. The sources also mention something called pruning.
Ah, pruning. Yeah, that's mainly for individual decision trees, actually, though related concepts can apply. It's like trimming branches off a tree.
To stop it getting too overgrown, too complex.
Exactly. You cut back parts of the tree that don't add much predictive power or that might be based on noise in the data. Helps prevent overfitting in single trees.
And there was a specific method, cost complexity pruning.
Yeah, that's one way. It involves a parameter, usually called CC-alpha, to kind of balance the tree's error rate against its complexity.
Gotcha. And with random forests themselves, can you tweak them? fine-tune performance.
Oh, absolutely. There are key hyperparameters, things like nestimators, just how many trees are in the forest.
Okay, more trees usually better, but slower.
Generally, up to a point. Also, max depth, how deep each tree can grow, and things like min sample sleeve or min sample split, controlling how many data points you need to consider making a split or forming a leaf node.
So you can control the complexity and behavior quite a bit.
Definitely. Adjusting those can really optimize the forest for your specific problem.
So thinking bigger picture,
Yeah.
this idea of combining many slightly different models.
It really is fascinating, isn't it? How taking multiple, maybe individually imperfect perspectives or models and combining them.
Often leads to a much more robust and accurate result than relying on just one.
Exactly. It's almost a philosophical point, you know? It applies way beyond just machine learning algorithms. Relying on a single viewpoint can be risky. Combining diverse inputs often gets you closer to the truth. Makes you think, doesn't it?